MSA studies performed for all measuring instruments specified in control plans of the critical characteristics. If measurement variation is not controlled may result in false decision regarding to product or process quality. MSA conducted in validation phase of APQP and also after launching a production process. Standard calibration procedures do not address the issue of measurement system variation. PPAP states that the organization shall have applicable MSA studies under bias, linearity, stability for all new or modified gauges, measurements, and test equipment. What is measurement system analysis? A tool to identify part-to-part variation between a pressure variation, equipment variation in a measurement procedure. Measurement value equal to actual value plus variation of measurement system. Total variation is product variation plus measurement variation. Measurement variation is equipment variation plus operational variation. Normally, repeatability is called as equipment variation, whereas reproducibility is called as between operational variation also. Good measurement system needs adequate discrimination, process under statistical control, accuracy, precision. Where does MSA is taught? Critical features are determined by the FMEA based on RPN indicators and put into the control plan during the design APQP stage as below flowed. Product engineer determines the critical characteristics, then he decide required resolution. Functional team considered the entire measurement system for the characteristics. Then metrology determined what equipment is available with them. When should we apply the MSA studies? Normally when new gauges are purchased, when new gauge is modified or serviced after, when new gauge SOP is introduced. Main factors affecting a measurement system. Measuring instruments. Gauge or instrument itself and its mounting block supports are fixers. Operators. The ability of a person to perform the measurements. Parts. Some items are easier to be measured than others. These affect the precision of the measuring systems. What is observed value, reference value, and true value? Observed value. Value taken by operator on shop floor with shop floor measurements. Reference value. On same part, value taken in standard room with standard room instruments. True value. Reference value may be considered as true value. Accuracy. Closeness of observed value to accepted reference value. It is normally addressed with calibration. Please look at the picture image. Accuracy but not precise. On average, the shoots are in the center of the target, but there is a lot of variability. Precision. Closeness of repeated readings measured on a part is called precision. Addressed with gauge are under study and more. Precise but not accurate. The average is not on the center, but the variability is small. Type of measurement system errors. Accuracy error, bias, stability, linearity. These are all determined by calibration. Please the image you can see. Precision error, repeatability, and reproducibility. Determined by performing R&R studies. Now we see bias. Bias is the difference of value between average of observed measurement value and the reference value. Action for bias to accuracy we have to increase the. Please see the images. Normally you can see the trials, three trials, and its difference in the bias. That is what I have interpreted in the image. Linearity is defined as the difference in bias value throughout the measurement range for which the gauge is intended to use. Consider these three trials. Normally the reference value is 50. My observed value is 50.01, bias 0.1. For 100, observed value 100.02, bias 0.02. For 200, observed value is 200.05, bias is 0.05. The above bias value is increasing order. The linearity may be increasing, decreasing, or constant linear. If linearity problem appears, we have to rebuild or replace gauge or decide to use only for specific ranges. Stability, it is a change of bias over time. Stability is the variation in the measurement average over extended periods of time. Remains same gauge, same pressure, same characteristics of a part. This today I will take one reading. Tomorrow I will repeat the same reading at the same condition as mentioned above. You can see the difference. When stability problem occurs, ensure equipment is properly cleaned and maintained. Ensure environmental conditions such as cleanliness, noise, vibrations. Confidential interval. The actual size of a measurement part can be anywhere within this confidential interval. I will elaborate later on. What is adequate discrimination resolution, normally also called? Ability to measuring the smallest difference. Example least count of instrument used should be 1 by 10th of the drawing tolerance than it is. Number of distinct categories. NDC is a measurement of the variation in your sample parts. Condition for NDC. NDC is calculated for variable data and not for attribute data. NDC is calculated for gauge repeatability and reproducibility. NDC is not used in bias, linearity, and stability. NDC required minimum 5. If you follow adequate discrimination, then you get NDC minimum 5. Example, outer dia is given 10 plus or minus 0.1 above, means 20 micron tolerance given. If you check this dia with manual vernier caliper, then manual caliper least count is 0.02 mm or say 20 micron. With this we can check only 10 mm and not 9.9 and 10.01. Because manual vernier caliper can check 9.98 or 10.02 mm. So in this distinct category is 1 or say NDC equal to 1. If we check this dia with digital vernier caliper, then digital vernier caliper least count is 0.01 or say 10 micron. With this we can check only 9.99 mm, 10 mm and 10.01. We can't check 10.005, 9.995 with this digital vernier caliper. So in this distinct category is 3 or say NDC equal to 3. If we check this dia with digital micrometer, then digital vernier caliper least count is 0.001 mm or say 1 micron. With this we can check 9.991 mm to 10.010 mm. So in this distinct category is 20 or say NDC 20. Repeatability. It is the variation in measurements obtained when one measuring instruments when used for 2 or more trials by only one appraiser while measuring the same characteristics of the parts. Commonly referred to as equipment variation. Reproducibility is the variation in the average of measurements when 2 or more operators measuring the same characteristics on the same part by the same instrument. Commonly referred as appraiser variation. This is a variation due to measuring method. MSA fall into two categories, attribute and variable. Attribute normally used in the final inspection like pass fail decision, go no go, document preparation, customer service response. Variable continuous scale, discrete scale, critical dimension, and full step. Please see the difference between the calibration and MSE. Normally calibration conducted in controlled environment. The MSE is conducted in actual working place. Conducted using masters. Conducted using actual products and parts. Conducted by qualified trained people. Conducted by actual users like operators and QC inspectors. Check accuracy only. Here it checks accuracy and precision. Variation. Variation can be called as law of nature, like type of hands, length of fingers, and giving force, like so. Variation cannot be eliminated, but it can be reduced. Goal is to achieve maximum possible reduction in variation. Variable data gauge R&R. The AAJ has to recognize standards for gauge R&R. One is short form, 5 samples measured by 2 times by 2 different individuals. Long form, 10 samples measured 3 times by 3 different individuals. Types of gauge R&R study. There are basically 3 methods existed in performing MSc. Range method. This will provide a quick approximation of measurement variability, but it does not compute measurement systems R&R. Average and range method, R&R method. Gauge R&R is a well-known method for evaluating measurement systems. It breaks down the total process variation into part-to-part variation, appraiser variation, and equipment variation. Only crossed gauge R&R can be performed with this method. ANOVA method. ANOVA uses the standard deviation instead of range and hence gives a better estimate of the measurement system variation. It also quantifies the appraiser by part variation, that is, interaction between the appraiser and the parts. Gauge R&R can be performed with ANOVA methods. See below illustrations how to perform gauge R&R study. Now we look at conducting variable gauge R&R steps. X bar OR method. Here I am explaining. 10 into 3 into 3 cross design study is the most commonly used. Nested design not preferable. 10 parts are each measured by 3 different operators with 3 times different. That is what I explained as 3, that is 10 into 3 into 3. Let me start the steps. Check the instrument has adequate discrimination, that is equal to or less than 1 by 10th of the tolerance. 3 regular appraisers, process inspector to check the parts, but select skills level different. One observer should also be appointment to record the measurements. Take minimum of 10 parts. For product control situations, part must be selected but not critical to cover the entire process range as part variation is not included in the calculation of gauge R&R. For process control situation, selection of parts from the top, middle, and bottom end of the specification covering the entire range is critical. Measurement system should be in statistical control. That is, the process of the parts collected for study should have only common cause of variation or not the special causes. Identify the parts for the ease of data collection but remain blind to the operators. Only check on single dimension and number of rails should 3. Take instrument which is used for regular process inspection and should be calibrated. Parts should be collected over time. Take maximum on out-of-spec parts for also inspection. Parts should be given randomly to each inspector. Have the first inspector measure all the samples once in random order. Have the second and third inspector measure all samples in random order. Continue this process until all the operators have measured all the parts one time. This completes the first trial. Repeat steps 11 and 12 for the record number of trials made, that is up to 3. Enter the data and analyze your results. Now calculate the average XC and range RE for part 1 or 3 tiles of the appraiser A as below. Next, calculate XC and range RE for parts 2 to 10 on its 3 tile for the appraiser A as below. Calculate X bar A and R bar A. X bar A equal to average XA of 10 parts. R bar A equal to average RE of 10 parts. See the below calculations. Repeat for appraiser B and C on calculating average XB, XC and range RB, RC for parts 1 to 10 of their 3 tiles. Similarly, calculate X bar B, X bar C and R bar B, R bar C. X bar B equal to average XB of 10 parts. R bar B equal to average RB of 10 parts. X bar C equal to average XC of 10 parts. R bar C equal to average RC of 10 parts. Now part average. Calculate part 1 average of 3 trials of each appraiser A, B and C. Similarly, calculate for X bar B for part 2 to part 10. So, range of part averages. RP equal to maximum of X bar B minus minimum of X bar B. Then calculate the appraiser's grand average X bar bar P. X bar bar P equal to average X bar A, X bar B, X bar C. Calculate the grand range R bar. R bar equal to average R bar A, R bar B, R bar C. Now calculate X bar difference. X bar difference equal to maximum of X bar A, X bar B, X bar C minus minimum of X bar A, X bar B, X bar C. Calculate the control limits for range sort. Upper control limit equal to R bar into D4. Lower control limit equal to R bar into D3. D4 is a constant based on number of trials. Please note D3 is equal to 0 for up to 7 trials. Now calculate the control limit for the average sort. Average sort calculations are upper control limit equal to X bar bar P plus A to R bar. Lower control limit equal to X bar bar P minus A to R bar. Range sort. Draw the range sort. This is the first sort you should look at it. This is what repeatability or gauge varies. Each point in the sort represents the range between three tiles taken by an operator on a point. So there are a total of 30 samples on each point. Please confirm range sort is in control. That is, all the points with control limits, then the operations are consistent. The range sort is not controlled, then should either rerun the entire gauge or rerun just that operator. These special costs could be because of appraiser method instrument inconsistency. If the range sort is in control, then draw the average sort. X-bar sort shows the gauge's ability to distinguish between points. Each point on the X-bar chart represents the average of 3 trials taken by an operator on a port. In a gauge R&R study, X-bar chart to have many points out of control limits. What we would usually consider evidence that our process is out of control. Sensitivity is that gauge is capable of discriminating between different faults. The area within control limits represents the measurement error. Normally 50% or more of the average falls outside the control limits. Then it indicates measurement system variation is much small as compared to path variation. Hence, measurement system is capable of controlling these processes. If the average chart is not beating conditions, then the cost for the same should be found out and corrected and the data should be taken again. After the chart are working, then start performing their calculation of R and R. Calculate repeatability equipment variation. This is also within operation variation. EV equal to R bar into K1. K1 is based on number of trials. Calculate reproducibility operation variation. This is a between operation variation. Operation variation equal to x bar difference into K2 the whole square minus EV the whole square divided by N. K2 is constant based on number of trials. N equal to number of pods or equal to number of trials. Calculate gauge R and R. R and R equal to square root of EV square plus AV square. Pod variation. Pod variation is determined by multiplying the range of pod average RP by a constant K3. K3 is constant based on the number of pods. Calculate total variation. Total variation equal to square root of R and R square plus pod variation. Now calculate the percentage values of the followings. As below. Percentage total variation, that is process control decision. Percentage equipment variation equal to 100 EV divided by TV. Percentage of operational variation equal to 100 into AV divided by TV. Percentage of R and R equal to 100 R and R divided by TV. Percentage part variation equal to 100 PV divided by TV. Percentage tolerance for border control decision. Percentage equipment variation equal to 100 into 5.15 into EV divided by tolerance. Percentage AV equal to 100 into 5.15 into AV divided by tolerance. Percentage R and R equal to 100 into 5.15 into R and R divided by tolerance. Percentage part variation equal to 100 into 5.15 into PV divided by tolerance. Now we can see GRR acceptance criteria. Ideally, all categories should be in the green zone. Category steady variations. Acceptable less than 10%. Marginal 10% to 30%. Not acceptable if it is greater than 30%. Similarly for percentage tolerance also. Less than 10% is an acceptable measurement system. It means there is no issues. If it is between 20 to 30%, may be acceptable based on application and cost of measurement device, cost of repair. If it is greater than 30%, to be rejected. Try to improve or replace measurement systems. Now the number of listing categories is equal to 1.41 into PV by R and R. Acceptance criteria of NDC. If it is one, not acceptable, difficult to distinguish one part from another. 2 to 4, generally not acceptable. 5 and above, acceptable for gauge R and R. Now draw conclusions and make changes if necessary. The MSA is acceptable only if the GRR and NDC both are OK. Now, operator report interaction. It is a situation where the result of an operator's measurement technique is influenced by the part itself. For example, two operators measure a shaft diameter using techniques that are identical in respect except one. That is, operator A takes measurement at the midpoint of the shaft length. Operator B measures at one end of the shaft. Two shafts out of 10 have burrs on the ends. A pressure A measurement not affected by the burr, but a pressure B measurements should have been affected by the burr. This will result in an interaction between the operator and the burr itself. See the image of components of variation in a variable gauge R&R study. Total variation equal to process variation plus measurement variation. Process variation is part to part, whereas measurement variation is reproducibility plus repeatability. Percentage gauge R&R for process control. Addresses what percentage of process variation is taken up by the measurement variation. This percentage study determines the measurement is good enough for SPC or statistical analysis. Can be used to control the process. The gauge cannot pass percentage study. It cannot distinguish one part from another within normal process variation or monitor process improvements, process changes. Now, percentage gauge R&R for product control. This study is used for deciding product acceptance or rejection. The study determines the measurement is good enough to inspect part products to its tolerance. We may have and conclusion 100% inspection is required or not. Addresses what percent of process tolerance is taken up by measurement variation. The gauge cannot pass percentage tolerance. It cannot determine if the paths are within specification. Few notes. First one, if gauge R&R as a percentage of total variation fails to meet the above criteria, but the gauge R&R as a percentage of tolerance range does not meet the criteria, then the gauge is acceptable. Note 2. 5.15 standard deviation accounts for 99% of measurement system variation. The use of 5.15 is an industry standard. Now, the interpretation of GR&R percentage with product tolerance. A variable gauge used to check agreed product characteristics of 125 plus or minus 3 mm has an R&R result of 22% of product tolerance. That means the gauge error can be up to 1.22 mm plus or minus 0.66 mm both sides for any given measurements. To ensure that non-conforming product is not accepted, the acceptance limit must be reduced by 22% to 125 plus or minus 2.34 mm. For repeatability problems, if our operators have the same repeatability and is too big, the gauge needs to be repaired or replaced. If only one operator, or in the case where there are no operators but several gauges and only one gauge is showing repeatability problems, retrain the an operator or replace the one gauge. For reproducibility problems, training and skill level of the operators must be assessed. Operators should be observed to ensure that standard procedures are followed. Note regarding the use of GR&R standard deviation. 5.15 standard deviation accounts for 99% of measurement system variation. The use of 5.15 is an industry standard. Historically, by principle, a 99% spread has been used to represent the full spread of measurement error, represented by a 5.15 multiplying factor. 99.73 per spread is represented by a multiplier of 6, which is plus or minus 3 sigma, and represents the full spread of a normal curve. About 68.27% of the values lie within one standard deviation of the mean. About 95.45% of the values lie within two standard deviation of the mean. Nearly all 99.73% of the values lie within three standard deviations of the mean. Please see the below process methods for how to conduct the MSc and few methods how we calculating the gauge variables study R&R study. Thanks.